Okay, so we will continue AES. So we have seen the few operations we have to perform on AES. So we will talk about the algebraic formulation of AES S box, the sub byte operation. So can you go to the slide, please? So for DES there was no explanation of the S box, how S box is coming, but AES there is a proper algebraic structure for AES. So there is algorithm to find the AES S box output. Now this is based on a finite field operation. So we are taking a field which is f2 to the power 8, which is basically z to x given by this irreducible polynomial x to the power 8 plus x to the power 4 plus x cube plus x plus 1. So this is a 8-degree irreducible polynomial. So this z to the power z to x means it is set of all polynomial whose coefficient are 0 or 2. So it is like a0 plus a1x plus a2x square. So this is basically z to x dot 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 of any degree. So n x to the power n, n could be anything. So where ai's are coming from z2, z2 is basically 0 and 1. Okay. So this is a polynomial whose coefficients are basically binary 0 1. Now if we take this polynomial px, which is a irreducible polynomial, if you take this polynomial and if you take this mod operation, I mean we take any polynomial in Z2 and we try to multiply this with this polynomial, then we will get a remainder polynomial, and that remainder polynomial so is basically, so if you take any polynomial ax can be written as some bx into px plus rx. So this Rx is basically of degree 7, because this is polynomial we are trying to divide by degree 8. So the Rx is degree 7. So that collection of this Rx is called, it will form a field. So it is a degree 7 polynomial. So it is basically some polynomial like a1, a0, a1x, a2x square dot 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 a7 x to the power 7. So all this collection. Okay, and each of these ai's are 0 and 1. So that's why, so there are 8 coefficients. So that's why it is size of this set is 2 to the power 8. So that's, this is basically f, this is called Galois field, this is f, this is finite field. So this is of size f 2 to the power 8. So this collection is this set, and this will form a field. So this is finite field, or it called Galois field. So this polynomial will use for this field, we will use for our AES S box. So if it is a field, we can perform the inverse operation in this. So inverse exists for a given x. So basically what we are doing, so we want to get the S box for AES. So this is AES S box. So it has 8 inputs. So this we are writing by A0, A1, A7 like this, and the output we are denoting by say B0, B1, B7. Okay. So this how we get B0s from A0s. So that we will discuss. So that is basically the AES S box operation. So what we do? So this is the this. Can you go to the slide, please? So this is basically the sub byte operation for AES. So sub byte. So it is taking input, say input A0. And it should give us the output like B0, B2, B7. So what we are doing? We are converting this into the field. So, how we can convert a 8-bit number into field? So, just we will just denote this by A1 plus A0 plus A1x plus. So, this is basically A0 plus A1x plus A7 x to the power 7. So, this is a field element Z. So, Z belongs to F 2 to the power 7. So, this is a Z is a field element. So, now this is a finite field. So, Z is having a inverse. So, that is basically, so if Z is not 0, then Z has the inverse. So, we denote that, we store that inverse in Z, inverse of Z. Okay. Okay, so then we just again store into this inverse into this, again this is a field. So, this again we convert into, this is again basically some sort of A0 plus A1x like this. This inverse is also a 7-degree polynomial, not A0, it must be some alpha 0, alpha 1, alpha 7. So, basically what we have? We have this A0 plus A1x plus A7 x to the power 7 into alpha 0 plus alpha 1x x to the power 7. This mod, that irreducible polynomial, should give us 1. Then this is the inverse of this, vice versa. Provided Z is not 0, it has a inverse. So, this is the inverse. So, now we store this alpha value here in A. So, A0, so A7, A6, A1, A0 we store into the, okay. So, now we have some constant. So, those constant are basically C value, C7, C6, C5, C4, C3, C2, C1, C0. We have 7 constant, and this constant is given by the designer. So, 0, 1, 1, 0, 0, 0, 1, 1. Okay, so this is the constant given by the designer. So, this constant we are going to add with this AIs to get the this BIs. This is affine transformation, we will come to that. So, now how to get BIs? Then, so this is 6. So, from 0 to 7, so basically we have BIs is basically, we have this formula AI plus AI plus 4 plus AI plus 5 plus AI plus 6 plus AI plus 7 plus CI mod 2, because everything is mod 2, and this is also, these are also has to be mod 8, because these indices have up to 7, 0 to 7. So, this is the formula to get the BIs. Then finally, we return this BI. Okay, so this is the algorithm. This is the code for algorithm for, this is the pseudo code for finding the BI. So, can you go to the slide, please? Yeah. So, this is basically the code we have discussed. So, we are taking the 7 bit, which are basically A0, A1, A7, A7. So, this is 8 bit. So, what we are doing? We are performing the binary to field. So, this is binary bit, it is field we are means basically A0 then plus A1x. So, that just the corresponding field element. Now, once we got the field element, and if it is not 0, then it has an inverse. So, we store that inverse, the field inverse of Z into Z again, and then we take the coefficient again in A, and then we have this constant. This constant is given by the designer, and then we have this BIs operations to get the output of the S box. So, we are basically, and this each of this index must be mod 8, because we only have A0 to A7, and then finally this should be mod 2, because this BI should be 0 and 1, then we return this. So, this is the, so let us take an example. So, suppose we want to have the output for 5 3. So, this is a 8 bit. So, 8 bit can be represented in 4 bit 4 bit. So, this 5 is basically in hex form, 3 is also in hex form. So, 5 is basically 0 1 1 0, and 3 is basically 0 0 1 0. So, this is our AIs. So, now if we convert into field element, it is basically 1 plus x square plus x to the power 6. So, this is the field element corresponding to this binary bits. Now, this we have to invert. So, this is non-zero element in the field, in the Galois field. So, this has the inverse, and we have to calculate the inverse, and this is the inverse for this. So, you can check by multiplying these two modulo that polynomial, that irreducible polynomial, and we can check this is 1. So, this is the inverse. So, now we store this inverse. So, this is also this is again a 7-degree polynomial. So, this has 8 bits. So, this will store into this, again we store into this AIs variables. So, A0, A1, A2, A7. Okay. Now, to get BIs, we have to get this C0s constant, and we B0 is basically A0 plus this, that formula we are going to use, and we put these values and we got 1. Similarly, we can calculate B1, B2, so on. So, this is basically giving us this BIs are basically this, which is in hex form ED. So, if we have input 5 3, then the output is ED. So, if this is x, this is y. If x is 5, y is 3, then the output is basically ED. Okay, so, this was we can verify from this table. So, if the input is x is 5 and y is 3, then we can check this output is ED. So, this is the table, but AES S box is not just a table lookup. We have a proper mathematical algebraic construction for finding the value for AES S box. So, after getting the value, we can store into the table, so that we can just do a table lookup. If it is not expensive than computing this executing this algorithm, then we will just look at the table and we go to that corresponding position and we get the output. But it has a mathematical explanation for finding the AES S box. Okay. Now, we will go for the how to get the mix, what is the mixed column operation for AES. This is also involves field operation. So, mixed column operation. So, this is also a field operation. So, it is basically it is taking a column, say S0j. So, AES is AES operation is state. So, this is a state of AES S01, S02, S03, S10, S11, S12, S13, S20, S21, S30, S31, S32, S33. Okay. Now, for mixed column operation, we are taking a column and we are converting into another column, which is the output of this mixed column operation S1. So, this is the 0th column S30. So, similarly, we take this column and we are converting into. So, if it is jth column means S0j, S1j, S2j, S3j. So, this is going to S0 j prime, S1 j prime, S2 j prime, S3 j prime. So, what are these elements? We will just come to know. So, this is the operation. Now, what is this primes? S are this new column. This will come to know. So, basically, this is basically the field operation on this So, basically what we are doing, this is S0 j prime is basically 2 into 2 means x into means this is the field operation, x into S0 j XOR with x plus 1 into x1 j, then XOR with S2 j XOR with S3 j. So, this is basically our first S0 j prime. Now, S1 j prime is basically, so this is symmetric. So, S0 j will be remain unchanged, then we multiply x with S1 j, then x plus 1 with S2 j, and then S3 j will remain unchanged. Okay. So, this is symmetric. So, S2 j prime. So, these two will be remain unchanged, XOR with S1 j, then we will perform this x into, this into means field operation. These are all 8 bits. So, this can be converted into field like summation of ai xi, then we can multiply this field operation under that mod, that irreducible polynomial. So, this is basically S2 j, then XOR with x plus 1 into S3 j. Okay. So, then again the last one is, so this is x plus 1 into, this is symmetric, S j XOR with S1 j XOR with S2 j XOR with x into S3 j. So, this is the formula how we get the this column mixed column operation. So, we have basically S1 S0 j, S1 j, S2 j, S3 j. This is transferring to S0 j prime, S1 j prime, S2 j prime, S3 j prime, and this is the operation we are doing. So, each operation is a field operation. So, this is x, this is a 8 bit. So, it can convert into, say, this is a 8 bit. So, this is a A7, A6, A0. So, this can convert into A0 plus A1x plus dot 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 A7 x to the power 7. So, this we multiply it with x, field multiplication, and field multiplication means under that Galba field f 2 to the power 8. So, it has to be mod that irreducible polynomial. So, again it will, after this multiplication, again it will be element in f 2 to the power 8. So, again we can convert into that a 8 bit. So, this is also same. So, all are 8 bits. So, we are doing the bitwise XOR. This is bitwise XORing. Once we got a 8 bit, we can do the bitwise XORing. These are all 8 bits. So, like this. So, this is mixture of field operation and the bit operation. So, bitwise XORing we are doing. Okay. So, this is the way how we do this mixed column operation. So, this is the So, this is basically our algorithm for mixed column operation. We are taking a column, the cth column, then we are converting into this operation we are doing, this field operation, and then we are bitwise XORing, and we are getting the new column. Okay. So, this is, we can take an example. Suppose our S0, we have a column like this. This is the first element. So, each element is a 8 bit. This is the first element of the column, this is the second element, this is the third element. So, this is the 0th column. Okay. Now, we want to see where it is going. So, this is 0 into 2 means it is just x. Okay. 0 into 02 means 02 means all are zeros. This is in hex notation, and 2 means 0 0 1 0. So, this is basically x, and 03 means, or only 3 means all zeros 0 0 1 1. So, this is basically x plus 1 in the this system. So, this is basically 2 into this is basically x into this is the field operation we need to perform. Then we need to perform, this is x plus 1 basically into this, and then these are all basically bitwise XORing. So, if we do that, we will be getting 47 for the first column of this. So, how we can check that? So, this is 87, 87 can be written as this, and this is x. So, if we multiply this, we will be getting this. Now, this is this has to be take mod, because everything has to be in f2 to the power 8. So, if you take mod, we are getting this field element, and then this is equal to this binary bits, and similarly we can calculate this x plus 1 into that, this is also binary bit. Then we are doing that, then we have this next 8 bit, next 8 bit. We are just doing the bitwise XORing with this, and we are getting 47. This is the first entry of that new column. Okay. So, yeah, so this is the operation we are doing. This is the mixed column operation. So, this is the mixed column operation we are doing. Can you please go to the slide, please? So, this is basically slide, please. So, this is basically the mixed column operation we are doing. So, if we just look at this matrix form, so we are taking a particular column and we are applying this transformation, mixed column transformation, we are replacing into the new column. So, this is sort of matrix multiplication. We need this when we talk about the inversion. So, this is sort of like this. So, this is we have a state, and this is a matrix, constant matrix, and then it will give us this, because when we talk about inversion of the AES, we need this information. Okay. So, this is the mixed column operation. Now, what is remaining? The remaining is the, so we have already seen the sub byte add round key, we have seen the sub byte, we have seen the shift row, we have seen the mixed column. Now, we want to discuss what is the key scheduling algorithm for AES. Key scheduling algorithm for AES. Okay. So, so this is basically what? So, it is basically give us the round keys, the key scheduling algorithm. This algorithm is public, only secret is the round keys, the key scheduling algorithm. So, it is taking that secret key shared between Alice and Bob, and this is the secret key, and this key size is 128 bit, because we are talking about AES 128. So, this key size is 128 bit, and it should give us how many round keys? We need to have 11 round keys. So, it should able to give us K1, K2, K3 dot K11, and each of these again a 128 bit. So, we should get a 128 bit round keys from this secret key. So, how we can get that? that is called key scheduling algorithm that we have to discuss. So, yeah, so let us talk about how to get this K1, K2, K11. Okay, so for this, what we will do? We have the key which is 128 bit. So, say we can again break it into, because we are doing the, we can again break it into bytes. So, 128 bit means 16 bytes. So, this is the key. So, 16 byte means we can just denote alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, like that, alpha 16. Okay. Now, we take the state wise. So, this is basically we store this in a state wise like this, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, alpha 8, alpha 9, alpha 10, alpha 11, alpha 12, alpha 13, alpha 14, alpha 15, alpha 16. Okay. So, this way we are storing this, and then we, what we do, we just yeah. So, these are, so what we do, we just take this. So, these are basically, we can denote it by k, k1, k2, but k we use for the round key, that is why we are denoting by this alphas. So, we just copy it into, so these are all 8 bits, 1 byte. So, if we can copy it into 32, so 4 means 32. So, this is a W1, W2, W3, W4. So, we just copy this, this is 8 bit, 8 bit, 8 bit. So, total is 32 bit. So, we copy this into this word, our each word is 32 bit, and we copied it here, we copied it here, we copied it here. Okay. And this is our K1, the first round key. This is our K1, the first round key. Okay. Now, this is 128 bit. Basically, first round key is the original key, the secret key, and that we are adding in the first sort of the round of AES. At first sort of AES, we are adding the first round key. So, this key we are mixing with the plain text, that is the first sort. Now, how to get the K2? To get the K2, what we do? We just apply. So, to get the K2, we have to get W5, W6, W7, W8. Okay. So, what we do? We take this W4 and we apply a G function. We will discuss what is this G function, and this G function, and we will take this W1 and we XOR with this, and this is basically W5. Okay. So, this is basically W5. So, we take this W4 which is 32 bit, we apply this G function, we will come to that what is G function, then again it will give a 32 bit, we XOR with this W1 and we get the W5. Okay. Then how to get W6? We take this W5 and we take this W2, we XOR with this and we get W6. So, basically W5 is basically G of W4 XOR with W1, and W6 is basically, now we have a W5, after this W5 XOR with W2, and then we take this once W6 is computed, we take this W6 and we XOR with this W3 and we got W7. So, W7 is basically W6 XOR with W3, and similarly once we got this W7, we XOR with this with W4 and we get W8. So, W8 is basically W7 XOR with W4. So, this is the way we calculate this W, and this is our, once we got this W5 to W8, this is our K2. Okay. Can you please slide please? So, this is the way we are calculating. So, these are our key, original key, this we are denoting by alphas anyway. So, this is our original keys and this we are copied into these W's. So, this is the first round key, and to get the next round key, what we are doing, we are just applying this with G, and then we got this, and then we XOR with this like this. Okay. Now, the question is how we get the K3. So, to get K3, we will do the same thing. We just now we have W5 to W8. We just copy this here. So, W5, W6, W7, W8. Now, we have to get W10, sorry, W5, W6, W7, W9, W10, W11, W12. Okay. So, how to get this? Similar way we have to do. So, we take this G, we apply on W8 and we XOR with this, we get. So, basically W9 is basically we apply G on this W8 and we XOR with this W5, and W10, once we have the W9 is calculated, W9 XOR with W6, and W11 is W10 XOR with W7, and W12 is basically W11 XOR with W8 like this. So, we got this is basically our K3, and similarly we continue this process until we get K11. So, basically these W's are giving us the key round keys. Okay. Now, the question is what is G? G is basically taking a G is taking a W which is 32 bit. 32 bit we can denote by B0, B1, B2, B3, each is 8 bit. So, what we are doing? We are just G consists of this is the G operation. So, G consists of 3 steps. First step we are rotating it. So, this rotation is basically so we are rotating it. So, basically this is going. So, if we denote by this way B0, B1, B2, B3. So, can you go to the slide please? So, this B0 is we are just making a rotation. So, this circular rotation, circular left shift we are doing. So, this is the first operation we are doing. So, circular left shift. So, circular left shift we are doing, and then we are performing the S box sub-byte operation on each of these. After this sub-byte operation on each of these, and then we are slide please. Then we are performing a sub-byte operation on each of that BIs. Basically, we are applying the AES S box, and then we are adding the round keys. We are adding some constant with this to get the this. So, these constants are basically this. Okay. So, these are the constant we are adding with the this with the BIs to get this G of this. So, this is the rotation, and we are adding the constant. These constants are given, and then we are getting the this BIs G of W. Okay. So, this is the operation for G. Okay. Now, we will talk about bit of inverse, how we can invert this AES. So, for that inversion, we have to think about how we can invert this operation like add round key, shift row, S box, and the mix column. So, for add round key inversion, just we will again XOR, because the XOR is the reverse of it. So, we will just XOR again. So, add round key inversion is simple. Now, what about the this sub-byte operation inversion? So, for sub-byte operation, so yeah, for shift row operation, for inversion is basically reverse. So, this is the original shift row operation. So, inverse shift row operation is just we do the reverse. Now, what about the inverse sub-byte operation? So, this is the sub-byte operation. So, sub-byte operation having this affine transformation. So, this is a affine transformation. After this we are doing this addition. So, this is basically affine transformation we have. This is the affine transformation we have in the sub-byte operation. So, now to get the invert, so we need to XOR with these BIs and then we will get this AIs, and then we have to apply the field inverse again to get back this AIs. So, this is the inverse for the sub-byte operation, and then we have to talk about the inverse for the mixed column operation. So, mixed column operation is basically this: we have these columns and this is the matrix we are multiplying. So, we are taking individual columns and then we are converting into a new column. So, for mixed column operation we can just have this inverse of this yeah. So, this is the mixed column operation. We have to take the inverse matrix of this and then it will give us the inverse mixed column. Yeah. So, this is basically matrix inversion we are doing. So, okay. So, this is a typical one round AES. So, here if we observe, so we are putting the plain text into the state and then we are applying the S box operation, the sub byte operation, then again we are storing into the state and then we are doing the mix shift row operation. We are shifting the position of this byte. This is byte wise operation. So, we are supplying the bytes here and there, then again we are storing into the state and then again we are doing the mixed column operation. So, we are just taking columns and then that matrix we have, then again this one and then we again adding the add round key. So, this is the again the state we are getting. So, there are many operations are involved. So, that makes AES secure. Okay. Thank you.